In section 3.2, we're going to continue talking about functions, and in particular, we're going to look at properties of a function's graph. First, let's review the concept of a y-intercept and that of an x-intercept. A y-intercept, you may recall, is a point that is part of a graph that falls on the y-axis. The y-intercept would have 0 as its x-coordinate, and then some real number b as its y-coordinate. On the other hand, an x-intercept is a point that lies on the x-axis and is part of the graph. What's true about x-intercepts is that the y-coordinate would have a value of 0. It's possible that some functions may have multiple intercepts, as we'll see in future examples. Let's look at how to compute the x and the y-intercepts for the following two functions. In the first example, f of x is equal to x squared minus 2x minus 8. To find the x-intercept, we will set y equal to 0. And we'll solve for x. Where is y here? Remember, f of x is just another name for y. So setting y equal to 0 is setting f of x equal to 0. So we have 0 equals x squared minus 2x minus 8. Now to solve this equation for x, we're going to factor the trinomial on the right-hand side. Two numbers that multiply to negative 8 and that add up to negative 2 are negative 4 and positive 2. Using the zero product rule, we write that either x minus 4 is equal to 0 or that x plus 2 is equal to 0, which gives us two solutions. X is either equal to positive 4 or x is equal to negative 2. That means that there are two x-intercepts for this graph. One x-intercept is the ordered pair 4, 0, and the other is the ordered pair negative 2, 0. So both of these are x-intercepts. On the other hand, to find the y-intercept, we set x equal to 0 and solve for y. So setting x equal to 0, we have that y is equal to 0 squared minus 2 times 0 minus 8. In this case, y is equal to negative 8. So there is one y-intercept, and it is the ordered pair 0, negative 8. In the next example, let me draw a little space here, we have a function g of x equal to 2. G of x is replaceable with the letter y, so this is really y equals 2. You may recall from previous lessons that this constitutes an equation of a line. In particular, it is a horizontal line. Because it's a horizontal line, we can think about the intercepts conceptually. Y equals 2 is a horizontal line that is 2 units above the x-axis. That means it's not going to intersect the x-axis at any point. So there will be no x-intercept. However, there will be one y-intercept, and you might recall that every y-intercept has 0 for its x-coordinate. Because y must equal 2 as a condition for the equation, in this case, the y-coordinate for the y-intercept must be 2. Let's look at working with a graph to determine the possible values of x and y, namely the domain and the range of the function. To find the domain of a function based on its graph, we are going to see the leftmost point on the graph and the rightmost point on the graph. So we're looking at how far a graph stretches to the left and how far it stretches to the right. And then we're going to write the x-coordinates as our two boundaries. On the other hand, if we're looking for the range based on the graph, then we're going to look at what is the lowest point on the graph and what is the highest point on the graph. Those are going to be the boundaries for the range. How low does the graph go and how high does the graph travel? Let's use this idea for the following two examples. In example A, we have a function that is not infinite. In other words, it doesn't extend infinitely to the left and to the right. So to find the domain, we have to find the leftmost point and the rightmost point. Notice that the leftmost point is open, meaning it's not included in the graph, it's simply a boundary. The rightmost point, however, is solid, and so that point is part of the graph. For the domain then, it looks like -2 is going to be a lower boundary that is not included, and +4 is going to be an upper boundary that is included. In other words, our x values for the ordered pairs in this graph go from -2 to +4 with -2 not included and +4 included. Again, we're looking at the leftmost point and the rightmost point, and in this case, the leftmost point is not included but serves as a boundary. Where did we get these values? The x-coordinates. All right, let's erase this so we can talk about the range. For the range, we're going to look at the lowest point and the highest point on the graph. Well, it looks like the lowest point on the graph is right here, and here we have an ordered pair -1, 0, and it looks like the highest point on the graph is way up here at 2, 6. Both of those are included points, and so we're going to say that the range goes from 0 to 6 with both of those boundaries included in the interval. Again, where do those values come from? We're looking at the y-coordinates for the lowest and the highest points. Let's move on to the next example. Here we have a graph that has 3 distinct branches. So, the entirety of all 3 of those branches constitutes the collection of ordered pairs that will form the function. This was a little tricky, so again, let's think about domain as going from the leftmost point to the rightmost point. In this case, this branch is going to continue traveling to the left indefinitely, and this branch actually will be stopped by this invisible line called an asymptote. So this invisible line here at x equals -3 serves simply as a boundary, but there will be no ordered pair that falls on that invisible line. Same goes for this other vertical asymptote. Here we have x equals +3 as a vertical line that serves as a boundary that will not be part of the graph. And then x values continue without bound to the right. So in essence, the x values in this graph include all real numbers except for x equals -3 and x equals +3. You see that between those two values, we have this part of the graph as well. So to say that the domain includes all real values other than -3 and +3, we're going to write this as 3 different intervals for which we find the union. So the leftmost branch goes from -infinity for x up to but not including -3. Then the middle interval will go from -3 to 3 with neither one of those endpoints included. And then finally, we have everything to the right of 3. I know this may seem like a weird way to say everything but -3 and 3, but hitting the speed bump over those two numbers is the correct way to write these intervals. Next, let's look at the range. Let me erase here so we can keep things clean. For the range, we have to look at the lowest point and the highest point and see if there's any points that are not part of the graph. We see here that this bottom branch is going to continue without bound, traveling downward. And then there's kind of a maximum point that is reached here in the middle branch. That is the origin. And then there's a gap. You see that between the top two branches and the bottom branch, we don't have any ordered pairs that form part of the graph. That means that there's going to be a break in the range. It looks like when y is 5, right here, when y is 5, we have another asymptote. And then the graph is going to continue climbing. So the range is going to go from negative infinity up to and including 0, and then it's going to pick up again at 5 not being included, and then traveling without bound upwards.